present our work on improving the implementations of linear layer. And it's a joint work with Wenling Wu, Tairong Shi, Lei Zhang, and Yu Zhang. In our work, we are focused on reducing the overhead of performing broad fiber and the Internet of Things require low-cost energy consume and the limited hardware resources. And this constraint make us explore how to implement the implementation of the symmetric ciphers components. And in the case of linear layer, the permutation can be regarded as a sequence of XOR operations. So our goal is to reduce the XOR count without using the auxiliary registers, since in some cases the registers are also resource intensive. And there are many relevant works on this topic. For example, to design a lightweight MDS metric, or like the previous presentation, to design a CPM metric. And also there are many other algorithms to optimize the existing linear layer, like the BP algorithm introduced by the Boya and the Pire in 2010. In the SPM network, buffer cipher can be written as the linear operation L multiplying by the input bit vector and produce the output bit vectors. On the other hand, if a linear metric is non-singular and the Gauss-Jordan theorem guarantees that we can decompose the linear layer as the product of elementary matrices. And there are three types of elementary matrices. We denoted as type 1, type 2, and type 3. For type 1 metric, and it corresponds to the row swapping operations, and if it swap the ith row and the jth row in identity metric, we denote it as the EILJ. And in the implementation, it can be achieved by swapping the line in the circuit. So this incurs no cost, and we need to focus on these matrices. And for the type 2 matrix, it corresponds to the row multiplication with non-zero constant. And since we are working on the GF2, so these matrices are also negligible. So for the type 3 matrix, it corresponds to the row addition operations, and if we add a row J of identity metric to the row, the number of type 3 matrices. And as the preliminary says, we can decompose the linear layer as the product of type 1 and type 3 matrices. But their order can be chaotic. So in the previous work, they introduced the commutative properties to reordering the product of type 1 and type 3 matrices. And it results. So there are many different implementations for the linear layer. And for example, the XOR implementation can be viewed as a XOR sequence, and it just can write as the xi equals the xj1 XOR the xj2. Here the j1 and the j2 is less or equal than I. In other words, we need to the registers are used to store the intermediate results at every step. And in contrast, the SXOR implementation can be written as the product of a permutation metric P and the sequence of type 3 matrices. Here, the type 3 matrices can be achieved by the in-place XOR, so there's no need for the actual registers. So our method is our idea is generate an initial decomposition first and optimize it with some properties. So first, for the generating and initial decomposition, the column transformation as well. And they also introduced the greedy algorithm, which will prioritize the row transformation that most efficiently reduce the number of ones in the matrix. So if no transformation can reduce one, then it will turn to the about strategy to avoid an infinity loop. They also introduced the swapping properties to determine whether the two type 3 matches can be swapped. And they also introduced the reducing properties to determine whether the joining type 3 matches can be replaced by a better implementation. For example, the left-hand side in the property 1 needs they first generate an demonstration first and enumerate all subsequence with length 2 or 3 and check whether of which of them can be moved into the adjoining position and check uh, which of them can match the reducing properties and finally replace them with less XOR implementation. So the first question is how to use the swapping properties. So for example, if we have the demonstration en dot ey dot ex and e0 and we want to determine the ex and the ey can be swapped into the adjoining position, and the original algorithm only check the two cases. The first is only moving the ex to ey minus one, and the second is only moving the ey to the ex plus one. And in our work, we slightly improve the search range. We will check all possible situations within the ey minus one and the ex plus one. But in fact, but it consumes a lot, so we want to discuss it here. And another key question is, are the reducing properties perfect? And for example, if we add one row into another twice, and the operations will be canceled out. And in other words, we have the extra properties that the ei plus j dot ei plus j equals the identity matrix. So as the slide show, we have many other reducing properties that are not included in the original piece. Content. For example, the right-hand side in the R3 and R4 are equal, but the left-hand side in the line can be swapped. So these two properties are equivalent. Type 3 sequence. And for two type 3 sequences, the S1 and S2, we define their equivalent if and only if there exists two permutation matches, PL and PR, such as the following equation holds that the PL dot S1 dot PR equals the S2. Here the PL and the PR can be regarded as the row transformation and the column transformation respectively. And next, we will show the problem of graph isomorphism in bipartite graph are related to the equivalent relationship. So the bipartite graph is a special graph that all vertices can be divided into two disjoint sets, V1 and V2. And every edge in the graph connects a vertex in V1 to a vertex in V2. In other words, the bipartite graph has no edges between the vertices within the same set. And so we can use a special adjacency metric to represent the bipartite graph. Namely, if there is an edge between the vertices in the i's vertex and the jth vertex in the another vertex set, the entry of adjacency matrix at position ij equals 1 and the otherwise 0. On the other hand, the graph isomorphism problem, or GIP, is an interesting problem in graph theory. The graph isomorphisms are adjacency preserving bijections between the sets of vertices. And the graph isomorphism problem asks to determine whether two given graphs are isomorphic. So here we transfer the equivalent relationship in graph views. We can regret the type 3 matrix, type 3 sequence as the adjacency matrix of bipartite graph, and let the two permutation matrix PL and PR as the vertex bijection within their own vertex sets. The 1 and S2 are equivalent, then the bipartite graph GA and GB are isomorphic. Here, the GA represents the bipartite graph generated by the adjacency matrix A. But unfortunately, it doesn't hold conversely, and it means that if the two graphs are isomorphic, but their adjacency matrix might not be equivalent. The reason is that the isomorphic mapping could cross the two disjoint vertices set, and however, we only care about the isomorphic map keep the vertices in V1 and V2 respectively. So the solution here is to color the graph, and in graph theory, the vertex color graph will be considered the color of vertex as an extra variable, and formally a graph with V nodes is said to be colored if each node in the graph is labeled with a positive integer node greater than the size of V. Then we can color the point. And we can obtain the theorems. And for the two type 3 sequences, S1 and S2, the S1 is equivalent to S2 if and only if the vertical graph of GA is isomorphic to the vertical graph of GB. Here, the most interesting here is we transfer the equivalentship in GIP. And the benefit is that we can use the GIP solver to reduce the XOR count. And here we use the GIP solver is the naughty and the trace. And we define the prime sequence and the compatibilities such that the S is equivalent to S dot. And Fs dot is less than the Fs. And if not, we define it as a prime sequence. Here, the F is the objective function we want to minimize, which is mapping the sequence S to a real number A. So if we want to search a low XOR implementation, we can just set Fs equals the length of a sequence. In other words, the prime sequence is the optimized or optimal implementation for equivalent matrix. And we also can define the set of all sequences as S and the set of all prime sequences as P. And the P can be divided into a union of several equivalent classes. And we can design an algorithm to search all equivalent classes by storing one element for each class. Here the question is, can we search all prime sequences or the equivalent classes for size n? And the answer is not, and we showed it as a theorem. The size of the equivalent classes is bounded by the following equality. And the lower bound is exponential, so we have to search the global optima to the local optima. And here's our new framework, which is combining the new swapping check and using equivalent check instead of the pattern check. And we will pre-compute the prime sequence as the green cells as the green cells, And as usual, we will generate initial decomposition and enumerate or subsequence with len 2, 3, 4, and we will pass it to the GIP solver or kind of hash table, which will return the prime sequence, equivalent prime sequence, and the corresponding mutation metric, and then we finally replace them with a better implementation. And here are our results. We find the 91 XOR count for AES miscolumn, which is keep the same with the GXOR implementation, uh, which is need the extra registered. And also our algorithm is flexible to search other implementation like the quantum circuit with lower diffs. And that's all. Thanks for your listening.